Hi, this is a continuation of greatest integer function. We will derive one obvious corollary. I should have done it in the last video, but I forgot. Now we will do that and then try to prove the so-called density of rationals in R. Okay. So we proved in the last lecture, given x in R, we said that there exists a unique m in Z so that m is less than or equal to x is strictly less than m plus 1. Right? Okay. Now what we want to do is notice that as an obvious corollary I have the following. My R is a disjoint union of m to m plus 1. M varies over Z. Okay. No. Notice that the RHS, that is the union, each is a subset of R, therefore it will contain an R. So only I have to prove, give me any x in R, I have to show whether x belongs to the union. Okay, right, that is very easy because what do I know? I know by the last result there is a unique m such that x lies in this interval, therefore it is. And why the union is disjoint? Next I have to prove the union is disjoint. Why? Because if m and n are different, okay, m plus 1 intersection, sorry, this intersection n plus 1 will be disjoint. Why? Assume m is less than n, then if x is common to that, that means x is less than m plus 1. But remember, m plus 1 is less than or equal to n. Therefore, this implies x is strictly less than n. But then x belongs to this. But then x belongs to n plus 1. That means x is greater than or equal to n. Okay. So these two things lead to a contradiction. Right? So that's it. So what you have shown is this is a disjoint. Next, what we want to prove is the so-called density of rationals. Okay, what does it mean in R? This means give me two real numbers a and b in R with, let's say, a is less than b. That means I have an interval of this kind, and look at the open interval. There exists, let us say, R in Q so that a less than or less than b. That means give me any open interval, I can always find a rational number. Don't worry about a and b. What it says, whatever open interval you take in R, I should be able to find one rational number here. Okay, can I find only one? If I can find one, I can find infinity many. Can you see that? Because you have an interval and you find an R, I am just magnifying it so that you can understand. So suppose there is an R, this one rational number, then In this interval I can find one rational number, and again in this open interval, okay, I can find another rational number. Now I can keep on doing. In this I can find one, 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 and so on, right? So once I can find one rational number, I can find infinitely many in the interval. Is it okay? Well, now I want to prove this. Now how do I prove that? As you may know, I am fond of working backwards. Okay, what does that mean? That means this is a theorem. That means there is a rational number between a and b. Let me try to find this. Any rational number, of course, is of form m by n, but usually students think m is any integer, n is a non-zero integer, but I claim I can as well assume n is a natural number. If you accept it, any rational number is of the form m by n, where n is a natural number. Yeah, is that obvious? Yeah, sure, because if you give me, for example, 4 by minus 5, but it is same as minus 4 by 5. Therefore, if you give me m by n, if n is negative, then that is same as minus m by minus n, therefore it is positive. Okay, therefore I can as well assume that, right? Therefore there exists a rational number of the form m by n, where n is a natural number between a and b. Therefore a is less than m by n and less than b. Now recall, we assume n is natural number, therefore it is positive. Therefore that means ma is less than na is less than m and less than n times b. So I have this interval, you gave me a b, now I have na and nb. Okay, I want to find some integer between in this open interval between na and nb strictly. Yeah, right. What is happening? Yeah, now forget this. Suppose I have an interval alpha beta, an open interval. Okay, can you think of a geometric condition which will ensure, that is on this interval I want you to impose a geometric condition, a sufficient condition, so that I am certainly I can find an integer k in this. Just to play with intervals, you will see that. Usually whenever I ask this question in my class, about 20% of the students come with the correct answer, but that's less in my opinion, but it's good, at least that way. Can you think of an answer? For example, take yeah, okay. The condition is if the length of the interval, namely beta minus a, beta minus alpha, is strictly greater than 1, then it will contain interval. This intuition, we can actually prove that by using greatest integer function. Okay, we are going to do it in a minute. Okay, assume that. Okay, now that suggests what I should do is I have to make sure the length of the interval na nb is greater than 1. What does that mean? N times b minus a must be greater than 1, right? But remember, m and n are unknown. But n is a natural number with what property? N times b minus a is greater than 1. Can I find such an n? Yes. By Archimedean property 2, okay, since b minus a is positive, there exists at least one n. So that n times b minus a is greater than 1. Right? Okay. Have you understood? Very good. Okay, now what do I want to do this? Now let us look at NA and B. Okay, I said geometrically if the length of the interval is greater than 1, I am sure to find an one integer. Why? Because remember, the greatest integer function says given any real number, there exists a greatest integer less than or equal to that number. So the next number should be greater than that, strictly greater than that. Okay, so that's the number we are looking for. So let us look at k to be the greatest integer, or in computer language I think see, I still forget, I am a mathematician, I think. Yeah. Okay, right, the greatest integer, that is k is a unique integer such that it is less than na and less than k plus 1, right? Therefore if I take k plus 1 as m, okay, you should be greater than na, therefore it can be on any side here, it should be strictly greater than na, it will be here. But now remember, k is here, k plus 1 should be to the right of na. Can k plus 1 be here? That is the one. It cannot. Why? Because the length from k to k plus 1 is 1, but that contains a subinterval na to nb whose length is greater than 1. So this contradiction shows m cannot be greater than or equal to, okay, nb. Therefore m has to be somewhere here. That is, m lies in the interval na to nb. Okay, this is a geometric argument. As I said, usually people are very wary of this argument, this kind of geometry, because intuition is somewhat less, and you may not even know how to turn the intuition into a rigorous proof, but we will turn it. Okay, now I claim, therefore what I am doing, I am going to claim m is strictly less than nb. I already know it is strictly greater than na. I want to say it is strictly less than nb. Suppose false, then what do I know? M is greater than or equal to nb, right? Okay, now I am through. Now let us look at 1. Now you will see the magic. You don't know why I am writing 1. You may not know what is m minus k. M minus k is k plus 1 minus k. So it may be a good idea to write this here, and okay, but that is equal to m minus k. But remember, m is greater than or equal to nb, and k is less than or equal to na. Therefore minus k is greater than or equal to minus nb, sorry, na. That is n times b minus a, which is strictly greater than 1. Therefore I have shown 1 is strictly greater than 1, an absurdity. Exclamation mark, not question mark. Yeah, so this shows my m has to be less than nb. Therefore I have na less than m less than nb. Since n is positive, therefore I get a is less than m by n less than b. Do you like the proof? That's it. We proved. We produce a rational number. Right? In a textbook, what will you do? We will not motivate this way. What we will do, we will start with this. Since b minus a is positive, this is where the proof will start in a textbook. Since b minus a is positive, by argument and property, there is a natural number n such that n into b minus a is greater than 1. The only thing is you do not know why you are starting. After this, we can check line by line. Now take k equal to the integral part of NA, then you do this, the proof is right. But what is missing is why that happened. And similarly, look at this proof. Okay, I wanted to say m is strictly less than nb. Okay, I said okay, take m to be greater than or equal to nb, it is here. Then I argued geometrically to show what is a contradiction. But a textbook will skip it. They would simply write take 1. Again you see it's a mystery. Oh yeah, you are writing. Yeah, I can write as something like 1.5 minus 1 also. Sorry, 1.5 minus 0.5 also, right? Why you wrote it? Okay, that's because we were guided by the geometry to write this inequality, and similarly we were guided by the geometry to choose an n such that yeah, the length of the interval NA to NB is greater than 1. See, this is what happens in mathematics. There is a lot of intuition. You build it, after that you make it rigorous. What you see in a textbook or a classroom teaching usually is very precise, well polished, line by line verifiable statement. But some you may not, you can understand the proof is correct, logically correct, but you may not know how the proof was arrived at. Okay, that's some problem. Okay, right. Now let us look at another thing. So I have proved. Now the next question I can ask is, does there exist an irrational number between any two real numbers? Okay, does there exist? And yes, the existence is about yes. Okay, right. That's very easy. What you do is to make two observations. You have to make use of them. How do you get I know something about rational number. I can find a rational number r so that a less than r less than b, right? So I want to construct an irrational number from a rational number. Okay, now what are the operations available to me? Addition or multiplication, right? So you start with an irrational number. Of course our favorite is 2, square root 2, right? Therefore let's look at a plus root 2. This is certainly less than b plus root 2 because a is strictly less than b. Now by our earlier result, I know there is a rational number r. Okay, r is in Q, right? Therefore it follows a is less than r minus root 2, which is less than b. And r minus root 2, can it be rational? Then in that case root 2 will be rational. Therefore this is irrational. So I proved it. Okay, sometimes students and some teachers say, let us look at, okay, root 2 times a less than r less than root 2 times b. This also sounds good, right? Then I will have a less than r by root 2 less than b. So I want to say this is in Q, right? If I take a non-zero rational, and an irrational, then RS will be irrational. But you told me there is a rational number. Well, okay, the luck would have it R could have been 0. If R is 0, I don't get anything. But that's not a problem. If R is 0, you have to take a second step. In that case, you look at a less than 0. Suppose R is 0. Then look at a here and 0 here, therefore I know. Okay, now I can do the same thing, a by root 2 root 2a and less than 0, therefore there exists another rational number r1. Okay, this between this I am multiplying both sides by root 2, right? Therefore a will be less than r1 by root 2, okay, less than 0. Therefore this will be an irrational number which will lie between a and 0, but 0 is less than b, therefore I still have the result. But the only thing is, if I multiply this, I have to be careful, I have to do it carefully. Okay, so pause, review, proceed. Okay, that's all today, that's enough. Okay, is there anything else I would like to say? I think for the time being it's okay, let us stop.